Welcome to my video series on PyTorch. Now I'm going to say straight off the bat that this is not like other tutorials. The biggest problem that I see with tutorials for machine learning online is that they try to teach you too much too fast. And so maybe you've done that before and you've trained some complicated network, you don't really know what you did, and then you want to go and solve your own problem. You've got something slightly novel and you need to make some changes to your model. And you don't quite know how to do it because you've only sort of been taught how to do a basic problem. I'm really going to try to focus especially on the fundamentals of PyTorch. So the main focus of this video is going to be the torch.tensor object. This is the meat and potatoes of everything you're going to be doing in PyTorch. A lot of people get into machine learning and they don't quite understand how to effectively manipulate torch tensors and numpy arrays. And it turns out the two objects are quite similar. So we'll start this tutorial by looking at the similarities between numpy arrays and PyTorch tensors. There's going to be many tutorials like this in the future. We're going to slowly build up into building complicated, powerful and novel machine learning models. So be sure to like, subscribe, join the Discord server, and enjoy.
So you want to train some AI? That's good, cause you came to the right guy. Understood? It's a lifelong journey, bro. This is it. Gotta build the fundamentals like Karate Kid. Wax off, wax on, torch on zeros and ones. 5 dimensions transposed. Yeah, you'll see it tons. Then concatenate. Then you celebrate. Torch.tensor is the key if you wanna be great.
So before we get started, when working in PyTorch, it's a good idea to have a separate Anaconda environment for working with it, because you don't want things to clash if you have packages that don't work with each other. And so whenever I work with PyTorch for doing complicated machine learning projects, I'm always in my own environment. So if you've installed Python using Anaconda, which is what I recommend, you would run the following command in your terminal: conda create, and then the name, and then your PyTorch environment. So you'd run that. I've already have my own environment that I'm sort of running it in. And then what you do is it's like a base Anaconda environment. You go to this web page here, PyTorch. It sort of tells you how to install it. I'll put a link in the description. And you choose the stable build, whatever operating system you have. There are options for a graphics card. I'm just going to deal with CPU in these videos. And it gives you the command here to run in terminal. So you can run that command, you'll have a PyTorch environment, and then you can install any additional packages that you need as well. Once that's done, before you run your Jupyter notebook in your terminal, you would go conda activate torch or PyTorch, whatever yours is. And so that means that you're in the PyTorch environment. And then if you were in your terminal, you just type in Jupyter notebook and run that. And then you have a Jupyter notebook in your conda environment, but I already have it open here, as you can see. And so then I'm importing torch, that's the PyTorch library, what it's called. I have numpy, matplotlib, and a little bit of timing to compare numpy and PyTorch in this video. So PyTorch essentially is a Python package that allows you, among many things, to train deep learning models in Python. And there's sort of two main libraries. There's PyTorch and TensorFlow. One's by Facebook, one's by Google. PyTorch is by Facebook. And they're comparable in a lot of ways, but I prefer PyTorch personally. I think it's a little less automated than TensorFlow. You have to be a little more careful about what you're doing. But in reality, what that means is that you're also understanding better what's going on. And so it helped me become a better coder of machine learning. And so the main focus of this tutorial, and what I think many tutorials out there miss, is that in order to use PyTorch well for machine learning, you have to have a fantastic understanding of the basic building blocks of PyTorch, and that's the torch.tensor. In many ways, it's similar to a numpy array, and if you want to be an effective coder in numpy, you have to be really good at manipulating arrays. Well, it's even more true in PyTorch. If you want to be doing complicated machine learning tasks and you want to innovate and you want to improve upon models out there, you have to be really good at using the torch.tensor object. So let's start by comparing NumPy and Torch a little bit. So the NumPy arrays and the tensors are similar objects in lots of ways, and you can use them the same in lots of ways. So here, little n means created in NumPy, and t is the Torch tensor. So I can run these, and of course, this is linspace, so it creates an array of 5 values between 0 and 1. linearly spaced from each other. And torch has the same function. It has torch.linspace. It goes from 0 to 1 in 5 steps. And I look at this. Here it's a torch.tensor, which is similar to an array, like I said, but it's got slightly different functionality, as we'll get into. These things can be resized in similar ways, and this is important with machine learning. So here I create an array that has 48 different elements in it. It just goes from 0 to 47, 48 different objects. And the same thing with torch. I can go torch.arrange to 48. But of course, you can reshape them to a shape that you want. So if I have 48 elements, 3 times 4 times 4 is 48. And so this turns it into, instead of a one-dimensional array, it's a 3D array where I have 3 elements and then 4 and then 4. So if I type in this instead, this is NumPy, it arranges this from 0 to 48 into a multi-dimensional array as follows. And of course, the torch.tensor has a similar thing, torch.arrange and then .reshape. And you'll be using this a lot, especially in machine learning. So it's useful to recognize the similarities between these two packages. But what's most important about NumPy and Torch, and what I would say is even more important for working in PyTorch than in NumPy, is the broadcasting rules of arrays. And most people code in NumPy and they don't really have an understanding of how this works. So we'll get into that. So there's lots of tutorials out there for this, but really it can be boiled down into a very simple thing, NumPy broadcasting. And you might wonder what that is. Well, that has to do with, you multiply 2 arrays together, and if they're the same length, of course, it does an element-wise multiplication of those arrays. So, for example, if I just have A equals np.array 1, 2, and B is, say 3, 4, I can multiply A times B, and I get the 1 times 3 and 2 times 4, I get 3, 8. So it's capable of broadcasting, but it gets a little more complicated when the dimensions aren't the same. For example, if I have, a 16 by 16 array and a 16 by 16 array, that's easy. It just does element-wise multiplication. But if the dimensions aren't equal, then there are rules, and there's ways to do it, but it's not trivial. So let's look at the general broadcasting rules. And I'll state it as sort of an abstract statement, but it makes a lot more sense when we go over examples. So you have arrays of arbitrary dimensions, and you start with the trailing rightmost dimension and you work your way left, comparing 2 different arrays. And the 2 dimensions are compatible when either they're equal or one of them is equal to 1. And so that might not make a lot of sense, but it makes total sense when you go over this example. So by the way, this is a much larger dimensional shape than you would get. This is a 6-dimensional array. Usually you're dealing with 2D, 3D, 4D arrays, but here's the 6-dimensional array and a 6-dimensional array. And it's 1 by 6 by 4 by 1 by 7 by 2. Usually with pictures, you might be 256 by 256 or 256 by 256 by 3. That's the 3 is the color channel. But here, just for an example, I chose 1 by 6 by 4 by 1 by 7 by 2. So let's see if the broadcasting rules work if I wanted to, say, multiply arrays that had these shapes together. So the first thing I do is I start from the rightmost dimension. So I'm right here. And there are 2 things that I have to go as I go from right to left. I either check if the dimensions or the size along those dimensions are equal or one of them is equal to 1. So here I have 2 and 2, so those are equal, so that's good. Then I have 7 and 1. These aren't equal, but one of them is equal to 1, so that's fine. 1 and 3, well, one of them is equal to 1, so that's fine. 4 and 1, okay, one of them is equal to 1, that's fine. 6 and 6, they're equal. And 1 and 5, well, one of them is equal to 1, so that's fine. So it turns out that these shapes, although they're complicated, they're compatible for multiplication, addition, any operation that you would do on these 2 arrays. So when you're dealing with tensors and multiplication and things like that, it's useful to keep these rules in mind when you're doing operations. And not only that, when you start getting used to these rules, you can use them to your advantage. Not only do you understand them, but you take advantage of the fact that you can multiply arrays like this to do things very quickly. So here's an example of 2 arrays. I have A and B. A is a 6 by 5 array, and B is just 0, 1, 2, 3, 4 array. And I can look at the shape of each one of these arrays. I can go A.shape and B.shape. And I'm wondering if they're compatible for multiplication. Well, I start at the rightmost dimension, 5 and 5, those are equal, that's fine. And then 6 and 1, well, one of them is equal to 1, so that means they're compatible for multiplication or addition. Well, what does that actually mean? Well, if I look at A on its own, it looks like this, and B on its own, it looks like this, so 0, 1, 2, 3, 4. And when I add them together, it's going to add the 6 and the 1. Those are going to be, stretched. So this thing here, 0, 1, 2, 3, 4, is going to be repeated as many times as these arrays are. It'll just be over and over and over, and then they get added element-wise. That's what this essentially means. And you look at the result, and that's exactly what's happening. I'm adding 0, 1, 2, 3, 4 to each one of these rows. That's why you can add arrays like this together. It's not element-wise, but the dimension where one of them has a length of 1, it gets duplicated. So in this case, this gets duplicated this many times, and they get added together. And of course, here's the same thing with PyTorch, with my tensors. I have A, which is a tensor at 6 by 5. I can look at the shape of this, and I can also look at the shape of B. It will also have torch.size 1, 5, and if I add these together, A plus B, it will do the same thing as NumPy does above. So all the broadcasting rules that apply to NumPy, which you might use all the time, they apply to Torch as well, and they're going to be even more important when you're programming in PyTorch. So you'll note that in the example above, each of these are 6-dimensional. That's fine. It turns out the arrays don't even have to have the same number of dimensions for broadcasting to occur. And that occurs where it automatically will fill in things on the left. So here's an example here. You want to scale each of the color channels of an image by a different amount. So you have red, green, and blue in a typical image. Those are the 3 color channels. So here's a 256 by 256 image, and you have 3 values for each of those pixels, the amount of red, blue, and green light, and that's this value here. So each pixel is it's got 3 different values that you scale for the colors. And then maybe you want to scale by red by 2, you want to make the blue by 1/2, and then the green is 1/3, for example. So that's your scale. And you only want the scale to be, represented once. So, here's my scale. I'll just put that here. All this says is for all the pixels in my array, I want to half the red, I want to 1.5 multiply by 1.5, the green, and then keep blue the same, for example. But I want to do this for all 256 by 256 pixels in my array. But you'll see that, the image is a 3D array, and the scale is just 3. It's just a 1-dimensional array. And the result, if I multiply image times scale, is going to also be a 3D array. So if the dimensions aren't the same, what it does is it will look at this last dimension here, and so 3 and 3 are equal, that's fine, and it's automatically going to put 1 and 1 here. So 256 and 1 are compatible by the rules above, like this. So what it will do is it will broadcast this thing here over and over to all the different pixels in the image. Remember, each pixel is 3 values. So I can multiply image times scale. So here I define my image. It's just random numbers. That's fine. 256 by 256 by 3 and my scale. And I can look at the image like this. If I type it correctly. So here's my image. It's, you can see it's a 3D array. And so this is the first pixel, red, green, blue, light. Second pixel, red, green, blue, light. And what it's going to do is it's going to take this array here, multiply this by 0.5, this times 1.5, this times 1. This times 0.5, this times 1.5, this times 1. It's going to do that for all the pixels in the array, and that's because broadcasting allows us to do this. And so I have image and scale, and I just take result as image times scale. It will scale all the pixel values accordingly. And my result, as it turns out, is fine. It works. It's okay. So even though I have a 3D array and a 1D array, I can still get a 3D array as a result. Here's another example that's sort of important. This is really what you'll get into when you're dealing with images in PyTorch. This is what I do all the time. And so suppose you have an array of 2 images. So if you have each image, right, you think of images as 2D arrays. Well, an image is a 3D array because of the color channels. There's 3 different color channels. The images are 256 by 256, and then I might have 2 different pictures. And so I have a 2 here. That's sort of the batch dimension in PyTorch. And so it's a 4D array for my array of images. And then my scales is also going to be a 4-dimensional array. I want to scale the color channels of each image by a slightly different amount. So maybe the first image, I want to scale it by, this amount here. And the second image, I want to do slightly different scaling for the pixels. And so I have a 2 and then 1, 1. Remember, 1 and 256 are compatible here. And then 3 at the end. And so my image is just a 2 by 256 by 256 by 3. That's my array of my images, and my scales Well, I'm going to list them as follows. I want the first image to be scaled as 0.5, 1.51, so red gets halved, green gets multiplied by 1.5, blue is the same, and the second image, well, maybe red gets multiplied by 1.5, green stays the same, and blue is 0.5. And then I reshape it so it looks like this, a 2 by 1 by 1 by 3, so that all the, like, this dimension is compatible for the two images, but because these are different here, each image gets scaled by a slightly different amount. It's really important to sit and think about what's going on here. And so I reshape it. Remember, this is just a 1D array here, this, or tensor here. And then I reshape it so it has the 2 by 1 by 1 by 3 shape. So it's a 4-dimensional shape like I have here. So if I actually look at my scales like this is going to be distributed across the first image to scale all the pixels in the first image by the same amount. And this will do that in the second image. So I have my scales, I have my images like this, and I multiply, and it's done correctly. So the first image is going to be scaled by, these three values here, and the second by these three values. It's going to be broadcast to all the pixels in each image. So that's a pretty complex operation that's being done there. That's, just a single multiplication that we're doing to our arrays. And this is so common when you're dealing with, PyTorch and machine learning and managing big data sets and everything going on at the same time. So you can also apply an operation across a dimension. So, this is very simple when you're considering a 1D array. Suppose I have 0.5, 1, 3, 4, and here I'm calling torch.tensor to make a tensor. It's just a one-dimensional tensor. It's got 4 values in it. And of course, I can take the mean of this tensor. I can take the standard deviation. I can find the max and min values. So I just separate them by commas. So when I enter this, it returns a tuple, 4 things here. So it will return the mean, which is a tensor that contains the value 2.125. That's the mean. The standard deviation of that array, the maximum, which is 4, and the minimum, which is 0.5. That's super useful in PyTorch. Now, operations across dimensions are sort of structured as follows. Suppose you have a 2-dimensional tensor, so maybe 256 by 256, and you want to compute the mean value of each of the columns of this array. Our columns would be this way. So you compute the mean of this column, this column, this column, this column, and then it returns an array as a result. So this is sort of important terminology. If you take the mean of a column like this, what that is equivalent to is taking the mean, this is how you would say it, across the rows. So you're doing means across the rows because you're coming down here like this and you're getting the mean here, the mean here, the mean here. So you're taking effectively mean across the rows. And the rows in a 2D array are the first dimension. So let's look at an example here. So here I'm going to create a tensor like this. It goes from 0 to 20 and I'm reshaping it. So it goes 0, 20, it's float. I'm reshaping it so that I have a 5 by 4 tensor that looks like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I want the mean of each column like this, so that's the first column, I want the mean. Second column, I want the mean. Third and fourth column, I want the mean. I'm taking the mean across the rows because I'm moving across the rows as I do that operation. And you can see that the first dimension, if I index like this 0, T0, it's going to give me the first row because rows are the first dimension in 2D arrays. And so if I want the mean across the rows to get the mean of each column, I would call torch.mean. I take T, and I want to take it across the first axis. That's the first dimension, which are the rows. So when it does this operation, it will take the mean across the rows. And I can run this, and I get, so 8 is the mean here, 9 is the mean here. Of course, it's distributed such that the middle value is also the mean. So that's how you would take operations across dimensions, and this is really useful for higher dimensionality arrays too. So here I create a tensor. It's just filled with random values. So it's similar to having, say, 5 images. They're 256 by 256, and then I have 3 color channels per pixel of my image. And suppose I want to take the mean of these images. Maybe they're all very similar. And I want to take that across the batch. So the batch are the number of images I have. So I have 5 images. And I want to take the mean values for each pixel across each of the 5 images. And we'll do that also for each color channel as well. So I can take the mean value across the batch. That's what I'm doing here. So torch.mean, feed in T, and I want to do it across the 0th axis. The 0th axis are the batches. So we'll take 5 images for each pixel, and for each color channel, it will take the mean. So it will take the mean of like the red color channel for all the 5 images, the blue color channel, the green channel for all 5 images, and it will do that for all the pixels, all 256 by 256 in the array. And that's what I call here torch.mean on this tensor t across the first axis. Well, you know, I don't have to put shape here, so it will do that operation. But if I look at the shape of the result of this, it will be 256 by 256 by 3 because I'm doing an operation across this first axis. So 256 by 256 by 3. I can also take the mean across the color channels. Maybe I want the average of the red, blue, and green power. This might give a measure of the brightness of each pixel. That could convert it to grayscale, for example, by taking the mean of the intensity of the red, blue, and green light. So here I take the torch.mean t, but this case, I'm not taking the mean across the 5, I'm taking the mean across the 3, which is the last axis. And so here I feed in -1, that will specify that I'm at the last axis. Remember, the last axis here is -1 and then -2, -3, -4. So I can use negative values to go from the final sort of dimension of the tensor here. And that's sort of common terminology. So here I take the mean across the color channels. And if I look at the shape, maybe that gets the brightness, like I said, you can take the shape and I have 5 by 256 by 256. So here I have 5 images that are 256 by 256. And I've maybe effectively converted them to grayscale images. I know that that's not the algorithm that typically does that, but this is sort of a Mickey Mouse way of getting the brightness of each pixel by taking the mean value of the red, blue, and green light. So another thing you might do is you might only take the maximum color channel value. So maybe you only want the red, green, or blue value that's the highest. So if red is highest, you take that. If blue is highest, you take that. And if green is highest, you take that. And you do that for all the pixels in each image of your array of images. And so this is done all the time in image segmentation models. I'll get into that in future videos, what exactly that means. But effectively what that is you take an image and you might decide which pixels correspond to a car. Or in my research, where I'm dealing with CT and PET images, it would be what pixels correspond to a tumor. And so this operation is done all the time. And so what you would do here, of course, here we're dealing with color channels, red, green, or blue. I have torch.max. So it will say, I only want the maximum value across this dimension. I have the last dimension, so that's the color channel dimension. So what torch.max does is it not only returns those values, but it also returns the corresponding indices. So that in the color channels where I have 3 different things, it would be 0, 1, or 2, corresponding to red, blue, or green. And so I can run this to get my values and my indices. My values, if I look at the shape of this, it's 5 by 256 by 256 because I've taken the max across the color channel dimension. I can look at the values and it will just be, some random numbers. But if I look at my indices, this is where it's interesting. It actually tells me, well, here it was, if it's red, green, blue, I don't remember the exact order, but here it might be blue, here it was green, here it was blue, here it was red where it's 0, here it was blue. So it also tells you what specific color was the maximum at that particular location. So this is a very useful function in PyTorch. So far everything has been sort of the same between NumPy and PyTorch. And the question is, where do the two packages actually differ? Well, you got to train machine learning models in PyTorch. That's one of the main goals of that package. And so what PyTorch starts to really differ from NumPy is in terms of automatically computing the gradients of operations. So for example, here's an example. So here's my value y. I'm just defining y as the sum. Suppose I have some vector x. I'm summing all the elements of x together cubed. It's just this operation here. So I sum over all the little xi's and I cube them. And if I want the gradient of y with respect to each xi, well, I can compute that manually, right? dy dxi, it's equal to 0 unless, you're at the value I. And so dy dxi, if I expand this sort of sum out, and you take the derivative with respect to xi, it's just 3xi squared. That's just the derivative of what's inside the sum. So that's an analytical formula. And what Torch does is when you do operations on a tensor, it can automatically compute the gradient. And so if I do this operation here, Torch will automatically compute this if I, compute y, for example. And I'll show you what that means here. So here I define a tensor, just like this, and I say it requires the gradient. So Torch is going to remember, okay, whatever operation I do on x, I'm going to remember, the gradient of what's happening here. So here I look at x, and it's 5, 8, 4, 6. It's just a 2-dimensional tensor here. And here what I'm doing is I'm taking x to the power of 3. So all the elements get cubed, and then I sum it together, and that's my value y, like this. And so y is 917. If you take all these values cubed and add them together, you get 917. And so if I want the gradient that's going on of all the operations that happen to x, well, y was the thing I computed. So here I'm computing the gradient of y with respect to x. That's y dot backward. So it will compute this value. It won't use the analytical formula, but it will use some numerical technique to get the gradient. And if I want the gradient corresponding to everything that's been done to x, well, that's stored in the x tensor itself. You might think it'd be stored in the y tensor. No, it's stored in x. This information is packaged into x. So you do a bunch of things to x externally, but it's all recorded in x, the x dot gradient thing here. So here I compute the gradient, and here I can print x dot grad, right? So x dot grad is this. This is always stored. This gets stored in x. And so I can double check this result, which was solved for numerically, by just computing this here. And sure enough, if I do 3x squared, I get the same values here. So the numerical technique that Torch is using to compute the gradient has given us the correct result. So you might think, well, why the hell is Torch doing this? Why do I want to compute the gradient of things happening to tensors, especially if there's easy analytical formulas? Well, as it turns out in machine learning, there is no formula as simple as this when you're computing gradients. But you still might wonder, well, why do I even need gradients in the first place? Well, in general, a neural network is just a function. Y equals f of x. And, in the way I'm writing this here, x is all the weights of your neural network. So a neural network can have millions and millions of parameters, and you adjust them slightly to adjust the predictions of the neural network. And what you want to do is you want to find, well, suppose I change one of these weights, how does the output of the network change? And that's exactly what gradients tell us. It says, if I change this, what's the change of the output? And so for complicated network structures where you don't have analytical formulas to have the gradient, PyTorch will automatically accumulate that to say, okay, for each weight that you have here, and if you change it ever so slightly, how's that going to change the output? And Torch will keep track of this. And so we'll get into this more in later videos. So again, that might seem sort of abstract now, but we'll get into that in later videos. But there's also some more additional benefits of PyTorch over NumPy. And the main thing is that PyTorch is actually faster for a lot of matrix multiplication operators. And so it's true with the CPU. I'm using PyTorch on a CPU right now, but it's even more true with a graphics card. And so I'll show you, I think it's about 2 times as fast, PyTorch on a CPU, but with a GPU, it's like 40 times faster. So anyways, here's Torch using a CPU. I have 2 1000 by 1000 matrices, and I'm going to multiply these matrices together using matmul. And so here I'm using the time library to get the 2 times, and I print the difference in times. And you can see this takes about 0.0098 seconds. Using NumPy, however, it takes about 0.028 seconds, so about 3 times slower using NumPy. So Torch has benefits for matrix multiplication, but of course there's a trade-off, right? You don't get nothing for free. And the reason why this is faster is because a PyTorch object, a torch tensor in computer language, is a heavier object than a NumPy array. It uses up more resources, more memory, more whatever on your computer to be stored so that it can do these operations faster. So if you have lots of torch.tensors, it's going to take up more memory on your computer. So you get faster operations, but the trade-off is that there's more memory that it takes on your computer. Anyways, I hope you enjoyed this video. Be sure to like and subscribe if you did. There's going to be more PyTorch tutorials in the future, and I'll see you next time.